Okay, sorry for the delay. Some technical issues. Welcome everybody. Welcome Edsko. Nice that you could join. Just a couple of words about your background. Maybe you have a strong background in functional programming, and even with a PhD in advanced type systems. And nowadays you work as a Haskell consultant with well-typed. And now I'm really happy to hear from you how to be lazy without being bloated.
Okay, thank you very much. Yeah, so I've been with well-typed for quite a long time now, maybe 8 years or so. But the last few years I've been consulting for IOHK, working on their Cardano blockchain. And this is a project that came out of that work. But my hope and expectation is that this work will be widely applicable well outside of the scope of that project. So this talk will be about a new library that has been released in typical hackathon fashion 1 hour ago, called nothunks. And I want to talk to you about, well, what this library does and why it's useful. So to this very day, one of the most contentious aspects of Haskell is still that it is lazy, right? If you ask people, what do you think maybe we should think about with Haskell, often people think, well, should it really be lazy? And the reason that people say that is not so much that laziness is not useful, but rather that laziness can often result in, or sometimes result in, memory problems, memory leaks that can be incredibly difficult to track down. Having said that, if you talk to people who have experience with strict versions of Haskell, for example, if you talk to Neil Mitchell or listen to Neil Mitchell talk about this, they have experience with strict versions and they are pretty sure, no, laziness is the right default. And for example, if you talk to John Hughes of QuickCheck fame, he will tell you that he now works with Erlang, and what he misses programming in Erlang is not so much Haskell's types, so much as the laziness in Haskell. Which to me, the first time I heard that was rather shocking, but there you go. Now, make of that what you will. I don't really want to go into the discussion here. To me, it's pretty clear that laziness is what we want, but the fact of the matter is laziness is what we have, and it can indeed lead to sometimes difficult to debug memory problems. And so in this presentation, I want to give you present a way in which we can address that problem. By way of motivating example, I want to start with a very simple first example, a very small application. So what this application is going to do, you're going to feed it a bunch of characters, and it's going to count how many characters you feed it, and it's also going to keep some statistics for every character. Now, in particular, the statistics that we're going to carry in this first version is just how many characters, how many times we see each individual character. So we have this update function here. Given an application state, which is just these two counts, and the new character that we saw, we just increment the total by 1, and we alter the element in the map for this particular character. If there was no entry in the map yet, then this must be the first time that we saw this character, and so the count is 1. If we did see it already, then we just increment the old count by 1, and that's the new count. Simple enough, I hope. So the initial application state has, we've seen no characters, so the count is 0, and the map is empty. We haven't seen any characters. And then the main function uses this interact, which is, you might not have seen before. What interact does is it gets the standard input as a string, passes that string to a function. That function can do with that string whatever it wants. That function is then supposed to give it back a new string, and that new string will be the standard output. So it dumps it to the console. And so what is the function that we pass to interact? Well, we're going to do a strict fold left, updating our application state for every character that we see. And then once we're done with that, we show the final application state, and that's what we return to interact, and interact will then dump that. So let's see this in action. If we echo AA, B, B, B through this application, it will tell us, well, we saw 5 characters, 2 of those were A's, and 3 of those were B's. Fine. We might write this application, we might even write some tests for it. We're happy with the functionality. And due diligence, we even look at a memory profile and we see it's lovely and flat. In a profile like this, when you look at this, there's some array or some buffers, blah, 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 but these are all perfectly flat. This is the profile of a program that's behaving well. So due diligence done, we're happy with this. we commit, and we're happy. The application is done. But now maybe a few months later, somebody comes around and says, well, you know what? Actually, I want to keep a bit more statistics per every character. I don't want to just count how often we've seen each character. I also want to know what is the last offset in the file of this particular character. When was the last time that this particular character was used? And so where before the statistics for characters were just an int, now the statistics is a pair of ints. The first int is still going to be the count, just like before. But the next int is going to be offset in the file, the last offset of the last time that this character is used in this particular file. And so we modify the type of statistics, and then of course we need to modify our update function. If this is the first time that we see this character, then there's no entry in the map, right? So in this case, the count is 1, just like before. And the offset is going to be, well, the old total, right? If we have seen 5 characters before, then the total was 5, and then the offset of this character also is 5, right? It's at index 5. So the old total becomes the offset, the last offset. Now, if we did see the character before, we are told the old count and we're told the old last index. We're not interested in that last index. We just want to override it. So we just increment the count by 1, just like we did before, and the offset is, like in the nothing case, is again the total. Does all make sense? Okay, good. So let's see this in action. We echo again AA, B, B, B through this example, and we're still seeing 5 characters. That's good. We still see 2 A's and 3 B's. Fine. But now additionally, we're also told, okay, the last index of an A was at index 1, and the last index of a B was at index 4. Okay, our test still passed, application still passes. PR review is done. It gets merged. Everybody goes on their way, moving on to other things to do. Then maybe sometime later, somebody discovers that actually our application has gone much slower for some reason. So it used to be fast, and now it's slow. What happened? And so maybe we start doing a git bisect, and we find, oh, actually, you know what? It was this particular change, right? When we're starting to keep track of the last offsets is what was causing the slowdown. Before, to process 100 megabytes of data took 2 seconds, and now to process that same 100 megabytes of data, it takes 16 seconds, almost an order of magnitude slower. So what gives? I mean, we're doing a tiny bit more work, right? We're keeping track of these offsets, but nothing that would justify an order of magnitude slowdown. So when you see something like this, chances are something went wrong with memory, right? You have a memory leak somewhere, probably, and you're spending a lot of your time collecting data or GCing or whatever. And indeed, if we look at the profile, we see the triangle of death, right? This triangle in this profile that we all know and love. When you see this in your memory profiles, oh, okay, I have a memory leak somewhere. This is not good. Now, the difficulty is, although this tells you you have a memory leak, it gives you almost no information on what causes the memory leak. Now, in this particular example, it tells you, okay, I have a lot of integers on my heap, and since my entire application is 20 lines of code, you know, it's going to be obvious, right? But in general, when you're debugging a large application, you know, just knowing the type or just knowing the function is often not enough. And going from these memory profiles and actually to finding the memory leak can be very, very difficult. So we had a regression, right? We introduced a change that introduced a bug. But the change is, this bug is very hard to debug, right? We can run our profile or whatever, but it gives us very little information to go on. And no tests failed, right? The program was still working. And that's awful, right? And this is often the case for memory leaks, right? Because your test suite typically doesn't feed it a ton of data, and so it is all small. And yes, it's using more data and more memory to run a test suite, but you probably don't notice. Now, when do you notice? You notice when your in production code starts crashing because it's running out of memory. So now you have an emergency on your hand. It's actually failing. Your server is failing. And at the very time that you have this emergency, you have a problem that is very difficult and time consuming to debug. So this is a bad place to be, and we want to avoid getting here. Now, I'm not the first to think about this. In 2016, Neil Mitchell gave a talk on this very same topic at Haskell X. It's a very nice talk. I recommend it, and you should go watch it. And the essence of his talk is that you could limit the size of your stack, You could also limit the size of your heap. It's a similar sort of idea. And the idea here is that if we limit the size of our stack or the size of our heap, our test suite will run out of memory much quicker, right? Because even though we only feed it a small amount of data, since we have a very small heap size or a slightly small stack size, the test suite will fail because it has a memory leak. And so indeed, we could do that in our application here. If we're feeding it, if we set this RTS flag here, M2M says maximum heap size is 2 megabytes here. Okay, and if we do that before our change, then we can count, no problem. And if we then introduce the memory leak, right, the change, then that limit is quickly exhausted and the program crashes. So this is better, right? Now, when we run our test suite on continuous integration with these limits in place, we will notice that our tests are failing much sooner, much before things break in production. So this is significantly better. But debugging these things is still difficult. So Neil suggested you could use the XC backtrace. So XC is a runtime flag that you can give your program. And what that does is that every time that an exception is thrown in your Haskell program, that exception is dumped to the console. So, and indeed, in this small example, that works just fine. That exception is shown on the screen. It tells you, okay, something went wrong in update. And together with the profile, that's probably enough for you to find the problem. But there are limitations to this. XC is often the output from XC is often very difficult to interpret because it dumps a ton of information to your console because Haskell programs tend to throw a lot of exceptions. And what's more, those exceptions get caught and rethrown. Every time they are rethrown, they get printed again. And typically, if you have memory leaks that are a problem, typically these are running server applications with lots of threads. Each of those threads might be throwing exceptions. It can be very difficult. In my personal experience, whenever I've been desperate enough to try XC, it's almost never been helpful. Moreover, we only get the problem once we exceed the limit. Now, we can set that limit quite small, but nonetheless, if we want to get a minimal counterexample out of this, then these limits are not going to help. So the rest of this presentation, I want to give you an alternative approach to this, which doesn't really compete with Neil's approach. It has a slightly different purpose, and I'll talk more about how the two approaches compare at the very end of this talk. But let's first see what we're going to do. So let's introduce some magic. We have our application state as before, and we're going to say deriving nothunks. Now, nothunks is a type class that is introduced in the nothunks library, and I'll talk more about what it does in a second. But for now, we're just going to say, okay, we have some new thing that we derived. And I'm also going to say, okay, we have this function called repeatedly, which is like fold L prime, like we were using before, but it does something with this nothunks business. And I'll show you what it does in a second. But for now, just think of it as fold L with some magic spring off on top. Now, what does the magic do? If we now run our code again, we get the moment that we get introduce this thunk, right? We're not updating something. We introduce the bug. We get a call stack, and this call stack is coming from Haskell stack. Now that has disadvantages and advantages, but typically I find Haskell stack traces much easier to interpret than XC stasis. Admittedly, you have to insert Haskell stack constraints in various places, but often this is much easier. However, much more importantly, you get this context. Now, this context is invaluable. This context tells you, and we read it from back to front. You have an application state, and that application state is fine. It's not a thunk. It was reduced to weaker normal form. But that application state contained a map. The map itself, also fine, not a thunk. The map itself contained a pair. Pair itself, also fine, not a thunk. However, that pair contained an int. That int was not fine. That int was a thunk. So this tells you immediately where your thunk is. And if you look at a context like this, you almost immediately see, of course, right? We have a map. This is a strict map, right? And we were using a strict map so that the elements of the map would be forced. We were not building up thunks there. But of course, if we're forcing a pair is lazy in the components, and so forcing the pair has no effect. So having a pair in a strict map is a red flag, right? And if you see a context like this, you almost immediately know what the problem is. Right, so just to go back to the example, in the initial version of the code, we had a map of ints. And so forcing those in still had a weaker normal form, by the strict map was fine, meant that we didn't build up any thunks. When we changed our statistics to be a pair of ints, the map was forcing the pair, but nothing was forcing the elements of the pair. And a context like this immediately points you in the right direction and makes it very easy to find and see what the problem is. So if we run our tests with these check in place, right, that we're not introducing any thunks that we weren't expecting, we catch the regression in the tests. We get a very helpful hint on where the problem might be. And if you combine this with something like QuickCheck state machine, that you can use to test stateful APIs, for example, you can you get a minimal counterexample out of it that tells you exactly, okay, with this small test case, we introduce a thunk. And I'll show an example of that in a second, in a few slides. Okay, so before I show you how the library works, I want to show you how the library could be used. So here's this function repeatedly with some magic sprinkled on top. And this is basically just for L, right? But with an additional check in there. And this is the additional check. After we've applied our function, the function that gets passed through repeatedly to update the accumulator, we do a check. And we do a check. And which check do? We call this function unsafe nothunks, coming from the library, which checks, are there any thunks in this value that we weren't expecting? It's called unsafe because observing if a value is a thunk, yes or no, is not referentially transparent. It breaks equational reasoning. And so it's useful for debugging, but you should not be using it for control flow in your code. Now, if we do find a thunk, then we error out, say, oh, you updated your state, but you left a thunk in there somewhere that you weren't planning on, so something went wrong. So this means you get that error the moment that you introduce a thunk, not when you exceed some limits, but immediately. If there was no thunk, then we just continue on our merry way and we process the rest of the list, just like for L does. Now, one point is very important. When you call unsafe no thunks on something like an expression like FBA, it is trivially a thunk, right? Which thunk? Well, the thunk that when you evaluate it would apply function f to the arguments b and a, right? So that would not be interesting at all. You would immediately error out. So you almost never want to apply unsafe no thunks to something that is not already a weak-head normal form. Of course, for L prime anyway wants to do that. So before we pass this b prime to unsafe no thunks, we first force it using the bang to weak-head normal form. That means it's not a thunk at the top level. Could still have a thunk inside there somewhere, of course. And so then we check if there are any thunks inside, and if not, great. And if there is, we error. Another example where you might use this, often server applications, for example, are a thin I/O layer on top of a a large pure layer. And often in this sort of circumstances, we might have an IO ref or an mvar or a tvar or something that holds on to our application state. And again, this sort of long-lived application state where you almost never want to build up thunks in there, right? So we could introduce a strict IO ref. What's a strict IO ref? It's just a wrapper around an IO ref. So when we read a strict IO ref, nothing different, we just read it. However, when we write the strict IO ref, whenever we write to it, we first force the value that we're going to write to weak-head normal form. And then before we write it, we do a check. Which check do we do? Well, the same one. We check, are there not any thunks in this thing that we weren't expecting? Here, we don't need to call unsafe because we're already in IO, so we can just call the regular function. But the idea is the same, right? Before we write to the IO ref, we check, are there any thunks in here? If not, fine. If there are, we throw an exception. And again, we get the exception the moment that we introduce a thunk. If the check completes, only then do we actually write. And just as a final example, this is a more pure code now. So suppose you have the state t monad. We can define a strict state t monad, which keeps the state in weak-head normal form at all times. By the way, common pitfall in Haskell, even state t.strict does not do that. State t.strict is not strict in the state. It's strict in something else, but it's confusing perhaps. So be aware of that. But anyway, this state monad is strict in the state. So getting the state out of this strict state monad is just get, right, with nothing to do. But when we put the state, again, we force the state to weak-head normal form first, and then before we actually put it, we do a check. Now this is pure code, so we have to rely on the unsafe version again, but that's okay. If there are no thunks in this state, then we put it, otherwise we error out. Okay. Now I mentioned that we can get minimal counterexamples out of this. So let me show you an example of that. Suppose that we have some sort of server and it's processing events. And we have two kinds of events, A and B. And the state of the server is just this pair of integers here. The initial state is just 0, 0. But we have this somewhat convoluted update function. So what does the update function do? If we see an A, we just count. So we just increment that A by 1. And we are careful not to build up any thunks here. If we see a B, we do something slightly more complicated. If A or B haven't reached 1 yet, then we just increment B by 1. Okay. However, if we haven't reached 1 yet, then if both of them have reached 1, then we increment B plus 2. There was a question: what is the additional argument to no thunks? So that is here. So I showed you this context that the no thunks is building up, right? So we have an application state containing a map, containing an integer, blah blah blah. And so it's building up the context as it traverses. We'll see more of this later. But as it traverses the data structure, it's building up this context larger and larger. And so this is the initial context that we pass it. So we just pass the empty initial context. The unsafe version just wraps this and gives it the empty one by default. Okay, so right. So if we look at this update function here, there's a bug, right? And in this case, of course, it's obvious. It's staring us in the face. In this particular case, we are forgetting the bang here, and so we're not forcing something that we should be forcing. Now, by the way, these sort of examples with lots of bangs in code are not actually a style I would encourage, right? I would encourage you to put bangs on data types, not on code. But this is not really a talk about how you make your programs leak-free, but rather how to find them. And I just want to keep the examples as obvious as possible. So don't take these examples as good coding style, but rather as examples of making things obvious, where things go wrong. So a minimal counterexample here would be, well, we need both A and B to reach 1. So we want to see an A event and then a B event, and then we need to reach this case. So we then need another B event. And indeed, if we plug this in, say, for example, QuickCheck state machine, I won't show all the details here. This is not a talk on testing. I'm happy to answer questions about it later, but but the idea between QuickCheck state machine is that you have some stateful API, in this case our server, and a model that tells you how the server should behave, and then you're going to compare the two against each other, send it a bunch of API calls, and you compare responses. So you must define some command type. These are the API calls that you're going to do, and in our case, that's just the event, A or B. And the response is the only response we're interested in here is, was there an error, yes or no? This string is just going to be the exception. Right? And the mock implementation, the model, is going to say there should be no errors ever. And then the real implementation might or might not throw an exception. And we're going to compare the two against each other. So when we apply an event for the model, we just call our update function purely without doing any thunk checks. And for the real one, we read our IO ref, we write to it. Remember, this is our strict IO ref, right? So this does the check for no thunks. This might throw an exception, we catch it, and if there's an exception, we just record that. So now if this throws an exception, QuickCheck state machine will say, oh, your real implementation is behaving differently from your model. And indeed, when we then run this test, we will get a minimal counterexample, this one. First do a B, then an A, and then another B. And if you do that, you will get a thunk, and we'll get a lovely context saying we have a pair containing an int that has a thunk, as well as a call stack telling you exactly where the thunk was created. So very lovely, minimal counterexample, clear explanation of where the thunk is, and a call stack. With this in hand, finding this and solving these leaks is often trivial. Now, you could have seen a different example. You could have also seen A, B, B, but you won't get larger examples, right? You won't get A, B, or something, because they could be shrunk to a smaller example that still has the same problem. So this is very, very helpful. So how does it work under the hood? So I told you we have this new class called nothunks. And nothunks has 3 methods. First is the most important one that you use as a user. This is the method that you call. And this list of string, again, is this context, right? Is the context that we're building up as we traverse through our types. W nothunks I'll talk about in a second, but it's often used in the implementation of nothunks. And then show type of is just a type that is meant to give a representation of a type as a string. And this is used to build up the context, right? The context was application state, and then a map, and then an int pair, and an integer. Those strings in that context come from this function, show type of. Now, all of these have defaults. So you could define an instance for nothunks without giving an implementation for any of these functions. And indeed, for the vast majority of your own types, that is the right thing to do. So instances for this class are often very easy. But of course, I'll show you how it works in this presentation. So let's look first at nothunks. So suppose that you are asking yourself, okay, how would I check if a pair contains any thunks? The moment that you pattern match on this pair, you're forcing the pair, right? So if the pair was a thunk, you would not notice. So we have to do something first before we pattern match. And normally in normal Haskell, you can't, right? It's not observable. So the library calls this check is thunk method, which is defined in the library, and does low-level GHG hackery to make this work. And it doesn't actually do very much. It depends mostly on a library called GHG HEAP for this magic. So we check, is this thing a top-level thunk? We don't check it doesn't contain any thunks at all, but just is this thing itself a thunk? If it is, well, then we find a thunk that we weren't expecting, and we return that thunk as this thunk info, and the context is the context that we're building up, right? And so we have the context that we were already constructing, and then we just add the type to the front of that context. So we found a thunk in something of type A. And just to show you, we just call this function here. Now, if this is not a thunk, at this point, we are justified in assuming it's in weaker normal form, and we are allowed to pattern match on it. So nothunks then calls this auxiliary function, w nothunks. And that's the function that actually does most of the interesting work for most types. So w nothunks, the w there stands for weaker normal form. You're allowed to assume the precondition is it's already in weaker normal form. You're allowed to pattern match. But now you must check, does not contain any thunks recursively in there somewhere. So when you provide instances for this type class, most of the interesting work happens in the definition of w nothunks. Now you can do that manually. You can do it using the generic instance, and there are also a bunch of new types that you can use for deriving via to derive these. And I'll show you each of these in turn. Let's first look at the manual instance. So suppose that we have this pair here, this new pair type, and it's a strict pair. So unlike the tuple that we looked at before, this thing is strict in both fields. Now, how do we check if this thing contains any thunks in there somewhere? Well, nothunks, the nothunks method already checked that it's not a thunk itself, so we don't have to worry about that. It's a weaker normal form, so we can pattern match. If we're allowed to pattern match, well, then it's easy, right? We have an X and a Y, and they just need to not contain any thunks themselves. So we just recursively call nothunks on those two components of the pair. And this all nothunks method here, all that does is it just runs all of the checks inside here. But as soon as one of them finds a thunk, it just stops there, right? We're not interested in finding all thunks. We're just finding the first thunk. So it just short circuits the evaluation. Okay, now, suppose that maybe for your type, you intentionally want to allow a field somewhere to be a thunk, right? For example, suppose that we have the int set here. In this int set is a set of integers, but additionally, we might also want to know the total of all the integers in this set. And maybe we don't always need this, but if we do compute it, we sort of want to cache the result. Now, this is easy to do in Haskell, right? We just make this a lazy int. And then when we, which will be set correctly, right? And then if we never look at it, that computation never happens. But if we do look at it, then we force it at that point, and then it's cached from that point forward, right? So this is a use of laziness. Now, but we want to allow this to be a thunk, right, by design. So in the instance for no thunks, we could just ignore this field, right? We just don't look at it. I beg your pardon. This is a typo here. This should be a call to a nothunks, not w nothunks. We don't know that this is in weaker normal form. Although we kind of know it from the type, but yeah, this is we should be calling nothunks here. Now, bear in mind that if you do this, it is dangerous, right? You have to be absolutely sure that you are not hanging on to some data in your cache total there that you should not be hanging on to, right? So anytime that you ignore a field like this, it is a call for careful thought and careful review. Because remember, although this is an int, you say, oh, it doesn't really matter if an int is a thunk, but that's not the point, right? The computation of this int could hang on to all kinds of stuff, right? So it's important that when you do this kind of thing, you are very careful and you very, think very carefully about what this cached field could hang on to. Okay, so those are two examples of manual instances. However, W nothunks also has a generic default. So this is the default implementation of W nothunks, and it's a bit complicated maybe if you haven't seen generics before, but the idea is quite simple. We translate the argument to a generic representation. So this is using GHC generics, and then we call a generic function of this thing. If you've seen GHC generics, this will look familiar. If you haven't, this will look probably completely alien. It's not really the point of this talk, so let me just show you how it's used. And so here, for example, is the instance for a pair, A, B, from the library itself. And as you can see, it doesn't do anything, right? No definitions for any method at all. And it just relies on generics to fill in all the details. And this works just fine. And since this works, because you can define an instance without defining any methods at all, that means that for almost all types that you define in your code, if you enable the derive any class language pragma, then you can just say, oh, derive in generic, nothunks, and you get a nothunks instance for your type for free without having to do any work. So this is often very convenient, and this is what we tend to use in practice for almost everything. But sometimes you don't want the hassle of having to define by hand, but you also don't want to have the default implementation. Sometimes you want to tweak it a little bit, what the instance does. And so the library comes with a bunch of new types that you can use for deriving via. So let me show you some examples. So maybe for your type, you only want to check if something is in weaker normal form. So you don't care if it has thunks nested inside there. You just want to check, is it not a thunk itself? So you can do that. There's a new type called only check weaker normal form. It has a nothunks instance, which doesn't at all depend on nothunks for A here, right? And so what do we do here? Well, remember, nothunks first checks is listing a thunk itself, and only if it isn't, if it's in weaker normal form, then it calls W nothunks. But this new type says we only are interested in checking if it's in weaker normal form. At this point, we have already verified that, so there's nothing left to verify. So in this function, we just say, okay, done, no thunks. And so, for example, a Boolean, if a Boolean is in weaker normal form, it's trivially thunk-free, right? So we can say deriving via only check weaker normal form, instance no thunks for bool. Now, there's another instance, this is coming from the library again, where we use this, and this is for function types. So for functions, by default, we only check if the function is in weaker normal form. That's a subtle point, and it's a design decision, and I'll come back to it. But it's an important point. It means, because when you define a lambda abstraction in Haskell, right, it can capture all kinds of things in the closure of the function, right? This function could hang on to all kinds of data. And by having this instance here, we only check if the function is in weaker normal form. We do not check if the function is hanging on to any thunks in its closure. And I'll come back to it. I'll explain in a bit why we made this decision. So we saw this example of int sets, right, where we wanted to check the set thing to be thunk-free, but we wanted to allow by design that the total should be have a thunk. And so if you can imagine that if you have a very large record with lots of fields that you all want to check to be thunk-free, but there's one field in there, there's a cache computation of something. Defining one by hand is a nuisance. So there is another new type in the library called allow thunks in, and it takes a type level list of field names. So you can say deriving via allow things in total, allow thunks in total of inset instance no thunks inset. And this will mean that you get the default instance that you're expecting. It will check all the fields except For the ones that you mentioned, for those it will ignore. They won't check. It is just, by the way, written by Alex Piali, somebody else working for IOHK. Okay. Now, we can actually bypass all this class stuff. We can look at the heap directly. So if we have a value of any type at all, by doing low-level hackery, we can inspect this value and check, are there any thunks in there? And so that's what the inspect heap new type does. And the w no thunks instance for this guy calls another check contains thunks, which does low-level GHC magic. Again, mostly depending on the GHC heap library. And so it checks, are there any thunks in there recursively somewhere? And if there are, it reports them. And if not, then it says, okay, this is fine. However, this has two drawbacks. One sort of pragmatic one and one fundamental one. The pragmatic one is that Haskell is a type erasing language. That means that at runtime, no types, right? You look at a value on the Haskell heap, it won't tell you what type it is. That means that although we can look at this value on the heap, if we find a thunk, we don't know what type it is. And so we don't really know where that thunk was. So we know it's somewhere inside the type of A, but we, how deeply nested it is inside this A thing somewhere, we don't know. So if you use inspect heap and you get a thunk failure, the context will tell you it's an A, but then inside there somewhere dot, dot, dot. We don't know. And so that makes debugging significantly more difficult. It's still useful, right? Because, for example, maybe you're interacting with a third-party library. A third-party library does not have any no thunks instances for the types that they define. And you don't want the hassle of having to give no thunks instances for all of their types. And so you just give a no thunks instance for their top level type, the one that you're using inspect heap, because inspect heap doesn't have, because it bypasses the class system, it doesn't need instances for all the nested types. So that's occasionally useful. Of course, if then you get a failure, you have a thunk there somewhere that you weren't expecting, now debugging is more difficult again, and so you probably end up defining instances for all the nested types as well. So you can avoid this. But yeah, I mean, occasionally this is useful, and this is how you use it, just like any other deriving via. But there is a more fundamental problem. And that is the main reason why this is not the main thing that we use. Sometimes you really must allow for thunks. For example, sequences. Sequences are from data.sequence, right? And sequences, data.sequence uses under the hood a data type called a finger tree. Now, if you haven't seen that, it's a fairly sophisticated Haskell data structure. I recommend looking at the paper. It's by Ralph Wiense. It's very nice. But for the purposes of this talk, the important thing to know is that a sequence, by design, has thunks in there. It does not always force every element of the sequence. And it's essential for that to be the case. Sequences have very good asymptotic complexity of the operations on the sequence, but it's only able to establish those bounds, those asymptotic bounds, by using by very clever use of laziness. So we really must allow for thunks inside a sequence. So if we just inspect the heap of a sequence, we would say, oh, there's a thunk there. That's bad. That's a problem. But that's not true, right? That thunk is there by design. So instead, what we want to say, okay, some thunks in the sequence are okay, right? Thunks in the spine of the sequence we must allow, but we do not want any thunks in the elements of the sequence. And so we can do that. I mean, this instance that I on the slide here is directly from the library, so it's trivial, right? It's very easy to define. So okay, I'll just translate the sequence to a list. So in other words, I don't care about the spine, but then check each of those values for thunks themselves. So the instance is very easy. But the point here is that we must be able to override the behavior of this check on a per type basis, right? And for that, we need type systems and type information. So if we just look at the heap, I just told you, the heap doesn't have any type information. And so we would not be able to override the behavior of individual types. So when you say inspect heap, if there's anything inside there that depends on thunks critically, for example, a sequence, you will get false negatives. So that's bad. So we don't want to do that. So we want to allow to override the behavior of the check for individual types. That is also the reason why I showed you the instance for function types, why this uses only check wicked normal form. Haskell does not use closure typing, right? Closure typing means that you, in the type of a function, record exactly what the type is of everything in the closure of the function. Haskell doesn't do that. And so that means that the type of a function doesn't tell you the types of the elements in the closure of the function. So we could check the closure of the function, but we don't know what their types of those elements are. So the only option we would have is to look at the heap, but then we can't override the behavior for specific types. So if your function would have a sequence in there somewhere, for example, you would get a false negative saying, hey, there's a thunk there that shouldn't be there. Well, actually, that thunk is there by design. So here the library errs on the side of caution and says, okay, a false negative saying that there's a bug when there isn't one is much worse than not reporting a memory leak when there is one. And so this is what we default to. Now, if for your particular application, you know that your functions aren't capturing anything that must have thunks in there, then you can define a new type around a function, give a custom nothunks instance for it that does use inspect heap, and then you can check your closures if that's what you need to do. Okay. So I'm going to wrap up. So when you have applications, you typically want your long-lived data to be thunk-free. So the original motivation for this code was the Cardano blockchain, right? So what is a blockchain? It's a distributed database, basically. Updates to this database come in as blocks. And when we apply those blocks, we update our database state. That's called the ledger state. And we don't want to be building up thunks, right? Because you could imagine that if you build up thunks as you apply every block, you can run out of memory, right? So the ledger state needs to be thunk-free. And so we use this library to check that. And even outside of the scope of a blockchain, I mean, lots of Haskell databases, servers use some sort of asset state database or some other server state that, again, is updated as the server runs, and we don't want any thunks in there. Now, in Neil's presentation, where he talks about the heap and stack limits, he talks about Shake. And in Shake, it's a build system, and there's a thread pool, which is sort of how the one of the long-lived data as Shake runs and processes your code. And Neil was keeping track of this thread pool because if an exception occurred, it allowed him to do some cleanup. But there was a bug. The thread pool was just a set of thread IDs. It wasn't not being forced, right? So whenever you deleted the thread ID from the set, it didn't actually delete it. It just created a thunk that, if it would be forced, would delete the thread. Therefore, this was hanging on to lots of thread IDs. Those thread IDs were hanging on to lots of stack. And so we had a memory leak of stack. Now, if we set a limit on this, you'd still find it, but it could still be difficult to find. And Neil says, I think it was a more difficult problem to find. However, if you say, okay, this thread pool is part of my long-lived data, I don't expect any thunks in there, then the moment that you do the first update to this, the first delete, for example, you will get an exception right there, right then. And it will tell you a context saying, hey, the shake state contains this thread pool, contains a thread ID, the thread ID was not forced, or something like this. Right? So it will point you to the right place immediately. So yeah, long-lived data, probably typically thunk-free. If you use that no thunks to verify that, you get an error the moment you create it. You get very clear errors. Problems are almost immediately obvious. And you get minimal counterexamples, right? If for some reason for your application, this thunk is only created in certain circumstances, if you then combine that with a QuickCheck, say, or QuickCheck state machine, you get very small counterexamples that tell you precisely, well, this tiny little program creates a thunk that you weren't expecting. Now, having said all that, I think this is a complementary approach to the heap or stack limits. So if you have the foresight to think, okay, this particular piece of my state should be thunk-free, then I think no thunks is a great way to do it. We have basically had zero problems with this in our service since in the Cardano blockchain since we introduced it. But of course, lots of these sort of or memory problems are more local problems, right? An accumulator and a function somewhere that you forgot to force, or something like this. And for those, you typically won't have no thunks checks everywhere. Although you could, of course, but if you don't, and typically you won't, then limiting the stack or the heap in the way that Neil talks about is still incredibly useful to find those sorts of more local leaks. Okay, we started a bit late, so I think I finished 50 minutes before time, which is what I was planning. So I want to allow some time for questions. So if there are, this is all I wanted to tell you. So if there are any questions, I'll be more than happy to take them now.
Yeah. I wonder if it's possible to do it at compile time, not at runtime.
Yeah. So yes and no. Some things are right. I mean, if we could say, oh, it would require a type system extension, and it's a good question. It's something I've been thinking about. It would be nice to be able to say, at the type level, right, or somewhere as a pragma or something, saying, oh, I want this thing to be this type to be strict. I mean, in the server example that I showed here, I had a pair of integers, right, and I solved it by forcing the pairs manually in the code. I actually think that's bad coding practice. I think you should introduce strict data for these sorts of things, and then rather than sprinkling your code with bangs everywhere, instead make sure that your data is strict. So it would be very lovely to be able to say to GHC, I want this to be strict all the way down, no matter how it's nested. But that's not so easy, right? Because if you define maybe your function, that if it's all monomorphic, right? If it's all type T referring to type T prime to referring to type T double prime, then it's not so difficult, right? GHC can just look at all these types and check that you have bangs in the right places. But what if you have a type that's parametric, right? Maybe a map, right? A map of values. Now I want to say, oh, yeah, a strict map should only be instantiated to types that themselves force this bangs everywhere. So that's much less obvious how to do that, right? So I think it'd be an interesting research question, and if somebody wants to do a PhD on it, I'd be happy to provide some motivating examples for you. But I think it's not all obvious how to do that.
Okay. Yeah. Thanks.
Sure.
Any more questions? I think there's some time left, so there's at least a break of 30 minutes now, so there's plenty of more time, seeing that we started late.
Is there an easy way to switch off the nothunks check if I say want to use it in my test suite but not when running in production?
Yeah, that's a good question. So the library itself doesn't provide an infrastructure for doing that, but yeah, typically that's what you want to do, right? You don't want to run these checks because these checks are pretty expensive. They traverse your entire data. So in production, you don't want to run these checks, right? These checks are primarily designed to be run in your test suite and continuous integration or whatever. The library itself doesn't give you any way to do that. But yeah, that's typically what you want to do. So in our cases, we have like a cabal flag that says, do I want to enable this check, yes or no? And if the flag is there, it just sets some CPP variable. And then in one place, we check the CPP variable. And if the CPP variable is set to be set, then we do the check, and otherwise we don't. And then everywhere else, we just depend on this one function. So it's CPP in one place and then nowhere else. And indeed, that's what you want to do, right? You don't want to be running these checks in production. Yeah. Any other questions?
So if there's nothing else, is there any more questions?
If there aren't, then I would recommend people to try it out. I really do think that this is immensely helpful. I used to think of space leaks as something rather difficult. It's occasionally still is, and I have various blog posts on gut-wrenchingly difficult examples. But in the vast majority of cases, I think this solves a large percentage of the problems. So yeah, do try it out and let me know if you have any problems.
Thank you, Edsko. I think that's some very impressive work. I've seen that you shared it on GitHub as well, just a couple of hours ago.
Yeah, it's on GitHub. It's on Hackage, so it's yeah, just in time for the hackathon. So indeed. All right. Well then, thanks everyone.
Nice talk.
Thank you very much.
Okay.